have time for a couple of questions. Professor Phillips?
So I wanted to ask about the application of these ideas in the financial markets. You described this high-frequency trading, and that the theory behind it, I mean, this is all news to me because I don't know anything about money, but you said that the theory behind the high-frequency trading is that you make the assumption that if there's a deviation, that the stock will return to the mean, and then you sort of bet on the fact that it'll return to the mean.
Yeah.
Now, what I'm wondering is, if the betting is on returning to the mean, why do people complain about high-frequency trading being an unstabilizing force in the stock market? Because it sounds like it should be a stabilizing force.
Okay. You see, there's a large number of participants. And I mean, I'm not an expert either. I know from my friends and I learn a little bit. And the fact is, okay, first, this is like a very large volume. I understand it's like 80%. So the people that trade long term are a minority. And no, high frequency trading has to be very fast, because if you are the second or the third, then you overshoot or something like that. In other words, this is not that you wait for 3 days and say, oh, the thing is deviating from its mean. This is for very tiny oscillations immediately, and the amount of bids that are done, I think, is much larger than what can it be tolerated. That's what I got from.
So in other words, it has the good sign, but the gain is
everybody says it has
high.
a good sign, but people don't like it. Yeah.
Okay, Professor Rodriguez.
Okay.
Sorry about that. Now it's okay. You mentioned that the distribution tends to Gaussian, right? In many cases...
In the Boltzmann equation,
in the Boltzmann, right.
Yeah.
In many cases, the diffusion, in natural cases, at least in an area I work, occur in fractal type of domains. Spatial domains are fractal. In those cases, distribution will not tend to Gaussian, correct?
I mean, distribution takes Gaussian in velocity, not in position.
That's correct. Will not tend to Gaussian in velocity.
Yeah.
That complicates dramatically the issue, correct? In the sense that you will have, among other things, distribution that frequently will not have a variance. Variance will go to infinity.
How is it again?
Frequently you will get into a power law type of distribution.
Yeah. Oh, you mean like a slow decay Levy process?
Right, a slow decay fat tail type of distribution.
Yeah, yeah.
And then for prediction processes, it has quite a level of complexity in the natural sciences, I think.
Yeah, okay, there is for instance, there are two things which are, that I gloss over. One is the interaction of the particles can be very complex. In other words, I say, okay, two particles hit, but there really is, you can have an interaction potential, you can have grazing collisions, so the interaction of the particles can be very sophisticated, and then things becomes much more iffy. Sometimes, the natural thing is that even some things are not even integrable and have so that may be one thing. The other is that the nature of the collision doesn't have to be totally restitutive, right? In other words, there are collisions where you have losses, right? And so then you have that. I think, in fact, there are I have seen a series of papers where for restitution coefficients which are some more sophisticated, you actually have power laws.
Right.
In fact, the literature is Bobilev. Bobilev is a very classical Russian mathematician that did a lot of Boltzmann, and he has worked a lot on power laws for Boltzmann, and I think was related basically to restitution coefficients. And there was another thing and another thing is that you may have, for instance, There is some other papers and so on where you, for instance, if you have two sizes of particles, you can have particles which are of some size, and they are knocking down particles of a smaller size. And then also that gives you a completely extra equation where there is some sort of different diffusion effect, and that changes completely the behavior of the stationary solution.
Or the spatial domain through which the diffusion is taking place.
The spatial domain, okay.
The spatial domain, say, it's a network like in rivers, and it's a fractal network. And if you but it's a very classical case in geosciences. If the diffusion takes place in that domain, then you get
yes, then you have a completely different. I think also, for instance, if you have complicated graphs,
that's right.
And you talk about diffusion in graphs, then it's another world. Yeah.
Thank you, Luis.
Okay, thank you. I think an interesting discussion took place there, and I am afraid we have to move on.
Okay.
Thank you very much again, Professor
Thank you very
Caffarelli.
much.